NanoHub U, online instruction.
Hey everyone, welcome to lecture 413. Now we're going to talk about thermal transport, and this will be an extension of the finite element method that we were using earlier, just applied to a different type of problem. So in order to first understand thermal transport, we have to know the three basic transport mechanisms, which are listed here, which are convection, conduction, and radiative thermal transfer. And so as you'll see in a minute, radiative thermal transfer is closely linked into optics, which is why we're even bringing up the topic in the first place. And of course, you can have a lot more insight and functionality if you can connect traditional optics with thermal transport in the same kind of multi-physics simulation. So just to briefly summarize what each of these methods or transport mechanisms is, convection is heat transfer by surface contact with gas or fluid molecules, which in practice you experience whenever you stand outside on a cold, blustery day and you feel the wind is biting into your skin. That's basically convection pulling heat off of your skin into the atmosphere. Conduction, by contrast, is more like when you touch a hot stove, because that's when you have a volumetric heat transfer through one material to another by propagation of phonons, which are essentially a unit of heat. And then radiative thermal transfer is more like when you stand in the sun on a sunny day and you feel your skin is warming from the sun shining onto it, because you not only have ultraviolet but also infrared radiation and visible, which is all being absorbed partially by your skin, depending on your skin tone, more or less extent, and partially reflected. And then whatever's absorbed, of course, heats up your body. And so basically, that's an example where the source is the sun and the receiver is your skin. But of course, there could be all kinds of different sources and receivers in practice, and we'll talk about other examples later. So to summarize the convection equations briefly, I already explained that it's like the wind on a cold day, and the transfer rate depends on two factors. One is called the convection coefficient, and that depends on a lot of factors, but definitely high velocity flow will increase the convection coefficient, and it kind of makes sense because more gas molecules are going by your skin if you have like a very strong wind than if you're inside, for example. So that H is dependent on wind velocity V, but it's also dependent on the gas itself, right? So if you're outside of air, there could be different gases that have lower convection coefficients. And also depends on the geometry of the fluid flow. So that's why I said the fluid flow environment. And then if it's happening on small scale, there may be micro and nanostructures that are impacting it as well. And then there's also the difference in temperature is very important. So whatever that delta T is will determine that rate of heat transfer. If the temperatures are very close, like if it's 70 degrees outside, it won't necessarily feel so cold, of course, because the delta T is very small. Now, going on to conduction, which is a little more complicated, which is, like I said, touching a hot stove. Basically, what happens is you have two heat transfer terms here, okay? And so you can look at it in either this way, which is kind of the rate of change of volumetric heat over time, right, integrated over volume, or you can look at it as basically two components at once. And so the first component is essentially like a surface flow of heat through some volume, like surface, right, plus the change in the heat within that volume itself. So that's written as Q dot ds surface integral. So this is a closed surface, that's why it has that little circle, plus this integral over the volume, Q dV. And so, of course, this choice of volume is somewhat arbitrary, but whatever that volume is going to determine what this U is actually depicting. And so, of course, you can try to model just part of a system with this, right? So, like, you could only model, for example, your hand touching the hot stove, not have any model for the hot stove necessarily, but then you need something to model Q, basically the rate at which heat is flowing into your skin. So that basically means that you can't neglect the role that the oven is playing, if you will. So then if we try to rewrite all these equations that I had here, and basically connect these two sides of the equation and basically apply the divergence theorem, then as you may know, you can take divergence of Q, and then you can convert this surface integral into a volume integral. And so then you would actually have 3 volume integrals. And so then if you combine everything together into a single volume integral, then you get this time derivative comes inside. So it's a d by dt of CVT, which is oftentimes written as this, assuming CV is not changing over time, which is usually a reasonable assumption. And then because this was on the other side, we turn this minus into a plus. And we have the divergence from the divergence theorem. And then this plus becomes a minus as you move it to the other side, becomes minus Q. And so then you can write this as like kind of like a more universal quantity that should always be 0. And so oftentimes people would write the equation just in this form rather than as an integral. Okay, so this is the differential form, if you will, of heat transport. And then as I mentioned before, you need to include a specific model for the heat transfer rate. And so we can use Fourier's law usually as a good representation of what this Q should be. And so Fourier's law basically tells us that the rate at which heat flows in equals the negative gradient of temperature times this thermal conduction coefficient, which is called K. And so this K here is material specific, of course, and sometimes there can be an additional thermal resistance, as it were, which is like the inverse of the K, which is coming from other sources, like maybe you don't have perfect contact with that surface, like the hot stove, for example. Actually, hopefully you don't, right? So then that can actually decrease your K. So then when you combine these things together, then you actually get this Q on the other side, so minus Q plus du dt is equal to the minus divergence of Q, which again is minus divergence of T. So actually you get 2 factors of divergence, which looks like a Laplacian, times K, and the 2 minus signs cancel each other. And then oftentimes you would rewrite this in order for everything on both sides to be a function of U, as basically T would be U over rho times CV. So rho is, of course, the material density, and CV is the volumetric heat capacity. And oftentimes these things would be combined into a signal quantity alpha. Of course, you could also write it the other way as a function of T in many cases, assuming that your material follows what's called the law of de Long-Petit, which means that the heat capacity is not really changing that much with temperature. And so this is essentially showing how all these things are connected that I just talked about. This is from Peter Chrystal's book. And so what it's showing is basically you have temperatures creating either boundary conditions or initial conditions, depending on the type of problem you want to solve. And then you have the kinematic equation for the flow of heat, right? So this is Fourier's law that I talked about. And then you have this balance equation, which is C dt by dt equals minus divergence of Q plus capital Q. And so this is basically the net heat generation plus heat flow through the surface from Fourier's law, and then they're being combined through the flux boundary conditions into a solution for the temperature. And so you can all see everything connects back. So in the next lecture, we're going to continue on this thermal transport modeling approach and get to results in the near future. Thank you.